Okay, so that concluded section 12.1 in our chapter 12 on vectors and the geometry of space. So in section 12.2, we're actually going to get into the concept of vectors now. Usually most people have heard about vectors a little bit or use them if you've had a physics class, high school physics class or something like that, but we'll take it right from the very beginning, so shouldn't be too bad. So some of the things we measure are determined simply by their magnitude. How big are they? For example, the mass of something or the length that something is, 12 inches, 1 foot, doesn't matter, 2 meters, something like that, or time, 2 hours, 30 seconds. Just how big is it? We only need to write down a number and name an appropriate unit of measure. However, we need more information to describe other things, such as a force, a displacement, or a velocity. In other words, what we need is to record a direction in which the force acts, or the body is displaced, or the body is headed when you're talking about force, displacement, or velocity. So if you've worked with vectors at all before, you might recall that we represent them as arrows. So we have an initial point P, a terminal point Q. You draw a line from the initial point to the terminal point Q, and you put an arrowhead on it at the terminal point. This is called the vector PQ, but then you put a little half arrow over it, indicating that we mean a vector. Or we just give another name, the vector V, which in this case is the vector PQ. Okay, now that's a vector just kind of sitting out there. If we want to talk about vectors in standard position, that means we have its initial point at the origin. And that's how we're going to work with vectors most of the time when it comes to calculus. Of course, vectors will have a position in space depending upon what they represent. But when we put them in component form, we are assuming we have placed the initial point at the origin in order to work with vector manipulations that we need to make. For example, if I think about that same vector V or PQ, I called it, from the point P to the point Q. Okay, if this vector can kind of be slid anywhere. I can pick it up with my fingers and just slide it right down here and make sure that the initial point's lined up with the origin. And now we put it in what's called component form. So the component form of a vector is really just the coordinates of its terminal point once the initial point's at the origin. So how do I get that? Well, there could be the components v1, v2, v3, but if I have a vector like this that went from a point P to a point Q, I get the first component by taking x2 minus x1, second component by taking y2 minus y1, third component by taking z2 minus z1. Okay, so this is the point, v1, v2, v3, but when I put these triangular braces around it, I mean the vector v1, v2, v3, which means it's a vector that has an initial point at the origin out to the point v1, v2, v3. And I just drew this, tried to show you like this arrow here is sort of this vector is sort of pointing out of the board at us a little bit to the right. So as I brought it down over here, you can see the shadow down in the xy plane. Okay, and that gives you a little bit of another way of drawing some perspective into some of your drawings. Okay, so component form. If a vector v, now in type or in reading your textbook, you're just going to see bold letters. Bold letters will indicate vectors. When I write it by hand, I just don't want to keep scribbling over the letter to make it bold. So what we do is we put it like a little half arrow above it. That's the same thing as seeing a bold V if it's in type. Okay. Now, if it's two-dimensional, then of course it would only have two components. This would be a vector that lies just in the xy plane, say. That's a vector in the plane equal to the vector with its initial point at the origin, its terminal point at the point v1, v2. Remember, the triangular braces mean we're talking about the vector. If the vector is three-dimensional, then it should have three components, v1, v2, v3. Now, how do I figure out the magnitude or length of any vector? It's simple. You just actually square each component, add them up, and then take the square root. Why is that? It's just the distance formula between 2 points. So if I'm looking at it as component form like this, that means its initial point was at the origin. So v1 minus 0 squared. We don't need to write that. Okay, but it's the same thing. Again, you can look at the previous sketch if that's confusing, but that's how that all works. One note here, the only vector with length 0 is what we call the zero vector. The zero vector means it's two components. If it's in 2 dimensions, it's 0, 0, or if it's in 3 dimensions, it's 3 components or 0, 0, 0. right? These components are scalars. This arrow above it means the 0 vector. These zeros are the scalar zeros, just representing the 0 for each component direction. All right, so example 5. Let's find the component form and then the length of the vector with the initial point P and the terminal point Q. So if you want to find the vector from P to Q, this is the notation. We're looking for the component form, V1, V2, V3, the component form because I'm looking at these triangular braces. So again, that's just x2 minus x1, y2 minus y1, etc. So for us, that's minus 5 minus a minus 3 right here, 2 minus 4, and 2 minus 1 are the components, which come out to be minus 2, 1. So the vector is like sliding the vector that started at P and went to Q down to where the initial point's at the origin, and now that's its terminal point, minus 2, 1. What's the length of that? You just square each component, add them up, take the square root. So in this case, it's 3.